Welcome back. In this lecture, we're going to continue generating arrays of random data. To be more precise, we'll stimulate data sets to resemble a process that follows a specific probability distribution, like the Poisson or the binomial distributions. At this stage, such an operation should feel very intuitive to you, since you already know how to create arrays using the normal distribution. However, some of you may not be as well versed in statistics and could find this lecture futile for their work. If that's you, feel free to skip to the next video. Without further ado, let's apply this technique using Python. To begin, consider this code cell. In it, you can see the NumPy's generator function and the PCG 64-bit generator applied for a fixed seed of 365. It's important to remember we need to declare the seed every time we want to generate pseudo-random data. Great! Now that we've refreshed your memory of why we need to set the seed again, we're ready to examine the Poisson method. To do this, simply write array rg.poisson and define the size of the output in the parentheses. The output is an array of zeros, ones, and twos because the default value for lambda is 1. If you're not familiar with the Poisson distribution, this means that over a fixed interval of time, distance, or space, we expect an event to occur exactly once. So it makes sense that the randomized array indicates 0, 1, or 2 occurrences over the same interval of time. However, in reality, we are often not interested in events that usually occur only once. That said, let's set the lambda argument lam equal to some other number, like 10. The end result is much more varied, since we see values ranging from 3 to 16. Statistically speaking, this result means that if we run an experiment 25 times, in one of those cases the event has featured exactly 3 times, even though it usually features exactly 10 times per experiment. The same thing applies to 16, which means that among the other 24 identical experiments we ran, in exactly one, our desired outcome appeared 16 times, rather than the usual 10. Overall, the variety of results makes this look more realistic, since we can never be certain what the outcome of the distribution will be like. In other words, fixing our expectations for obtaining 10 features for every experiment is not realistic. All right, another important distribution is the binomial distribution. It measures how many times a certain outcome can appear over a series of trials, where there are only 2 possible outcomes. We can once again copy the code we just wrote into a new cell and change the name of the method. This time we're changing it from Poisson to binomial. Different distributions require different parameters to compute. Since the binomial distribution doesn't rely on lambda, we can delete the argument. However, it requires 2 other arguments, n and p. The former is the number of trials we're running, and the latter is the probability of getting our desired outcome. Thus, to provide an example, we can set n to a positive integer like 100, and p to a decimal between 0 and 1, like 0.4. The result is a 5 by 5 matrix, where each element is the number of times out of 100 we've gotten our preferred outcome. We can observe that the numbers obtained are practically between 30 and 50. This means that on average, most of the outcomes are around 40. This is a result that could be expected, considering that we had set only a 40% probability of getting what we want on each of the 100 individual trials for a given experiment. Superb! Lastly, we want to stimulate the outcomes of a logistic distribution. We'll once again copy the code we wrote earlier and change the name of the method. This time, we're changing it to logistic. Since a logistic distribution doesn't require n or p, we can get rid of them. However, it does require location, written as just loc, and scale parameters. For the sake of this example, let's quickly set them equal to some numeric values like 9 and 1.2. The output represents another 5 by 5 matrix, where each outcome is a possible outcome of the logistic distribution with those scale and location arguments. Nice! Therefore, we conclude that we can replicate this code and generate an array of values that can be said to follow one from a large set of distributions, as long as we specify all the necessary arguments as we showed in these 3 examples. For a full list of methods and distributions we can use with generator objects, you can check out the NumPy documentation. A link to the correct page is provided as a resource to the video. Fantastic work! Now that we've learned how to simulate data from events that follow a known distribution, we can say we've mastered using NumPy's random generators. Thus, it's time to slightly shift our focus. In the next lecture, we'll move on from the simple statistical implementations to applications of random generators and explain why they're useful. Thanks for watching.